Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 47. We left over at how we can try to do solid welding between two different surfaces, and I think we had just illustrated that the greatest hurdle in solid phase welding is posed by the surface oxide layers and also oil films. The liquid films can be removed by heating in hot welding and by scratch brushing in cold welding. The oxide films can also be reduced to a certain extent by scratch brushing. Moreover, these oxide layers being hard and brittle fracture when pressure is applied, and a lateral movement is very useful in particularly ultrasonic welding to do this removal of the oxide layers, and basically they get fragmented and get into thick agglomerates at different regions of the particular surfaces, which is also good in ensuring that there is close proximity between the parent metal surfaces together. So, it basically results in more metal to metal contact area. So, an excessive oxide contamination is always harmful, resulting in poor joint efficiency, and we also saw that a solid phase welding done at room temperature does not really allow recrystallization and grain growth at the interface to happen. So, this reduces ductility of the joint to some extent, and an increase in the working temperature not only increases the ductility, but also eliminates some other defects. We also record that the phenomena of diffusion, though it has not been very well studied, also plays an important role on the performance of the sort of solid weld joints, and sometimes diffusion is used by creating a concentration gradient between the surfaces, so that there is some kind of migration of the atoms from one surface to other, causing an interspersing between the two crystal lattices together. So, we will now try to understand some of the principles of liquid or fusion welding. As the name suggests, is basically a technique where the joint is melted in both parts of the joint, and either there is a filler material which is same as the parent material or different, and it causes some kind of a recrystallization again because of the tendency of the material to solidify, and this solidification results in joining of the two parent materials. So, the fusion yielding process may either be autogenous or homogeneous. Metallurgically, if you look at the different zones, there are three such distinct zones which happens in such a welded part. The first zone is the fusion zone, of course. The second is the heat affected unmelted zone around the fusion zone, and the third is obviously the unaffected original part. And so, there is an interplay of transfer of heat across the fusion zone, the unmelted zone around the fusion zone, and also the unaffected zone of weldment. So, that because of this heat flow, there is a solidification, just as we observed in the case of casting earlier in great details, and because of the solidification, there is an aspect of strength which is involved in joining both the materials. So, if we look at the different important factors which are used for governing fusion welding, some of these factors would definitely be the characteristics of the heat source. So, whether we are using an electric arc or whether you are using induction mode or maybe a thermite material for creating enough amount of temperature, so that melting happens, would definitely determine as one of the governing factors the quality of the fusion welding process. Also, the nature of deposition of the filler material in the fusion zone, known as a weld pool, would also be very critical factor. The heat flow characteristics in the joint would be a very critical factor, because it would allow us to sort of estimate what is going to be the recrystallization level, what is going to be the grain sizing, resizing level, and ultimate yield strength of the joint. The gas metal or slag metal reactions in the fusion zones are of critical importance, because such reactions may create states which are highly brittle in nature, and it may result in some kind of joint failure, etc., because of chemical reactivity. And then the cooling of the fusion zone with associated contraction, residual stresses and metallurgical changes associated with this whole cooling process would also determine what is going to be the quality of the weld which is going to be there. So, the first characteristics here, as you can see, is the heat source, and we are going to try and estimate or evaluate some of the different heat sources or heating processes which are available in the welding. So, what are the different kind of heat sources that are available for liquid state welding? So, we have the electric arc, which is one of the most common sources in various arc welding operations. We also have a chemical flame, as in a gas welding, where you use some kind of an oxyacetylene gas and burn it. So, you can produce enough energy. You also have an exothermic chemical reaction called the thermite welding methods, where there is a typically a transition metal oxide, like let us say copper oxide or iron oxide being used with aluminum, which acts as a fuel particle, and there is a transfer of oxygen between the transition metal oxide and the aluminum, which results in an exothermic process. Okay. So, typically these are also known as underwater welding phenomena, because it does not need any free oxygen in air in order to do the burning. And then we have electric resistance heating, okay, where typically the applications could be in electroslag or other resistance welding processes. The whole automotive industry is geared around this electric resistance heating process, where sheet metals are typically spot welded to each other, in order to pull together as in a chassis of the particular cars. So, the general characteristics of these heat sources we will try to now understand and discuss more. So, let us look at the first heat source, which is the arc welding. So, let us look at this particular scheme here. This is an arc welding scheme. There is an electric source, there is an arc which is created between electrodes. This is the cathode, and then the workpiece is the anode in this particular case. As you may recall, and I am sure most of you have seen, the electric arc welding process is initiated between an electrode which is clamped onto a welding clamp. So, typically the electrode is clamped onto the electrode holder, and you may have also seen that the electrode is slightly broken from the surface and brought very close to the workpiece, and then suddenly you take it away, and then it generates a high current flow at the instance you are touching the material, the parent material, and then the moment you have taken out the electrode away, there is an arc which is stuck between the electrode and the workpiece. So, what exactly is happening? Let us assume that the electrode surface that we are considering somewhere here is a little bit rough, and there are many asperities which are there on the surface, and there is again a whole metal surface or workpiece surface which is again having these asperities. So, as we take the electrode in the the holder clamp very close to this surface, there are going to be asperity to asperity welding or locking which would happen, something like this. Okay. So, there are many such areas on the electrode which would actually have small asperity to asperity contact with the parent materials. So, in this particular case, it is more like a short circuit which would happen across a few asperities, and there would be something called the short circuit current which is generated, which is a huge current by the by, from the source onto the workpiece surface. So, typically the workpiece is also earthed, because all the current that comes into the workpiece should typically flow. So, it is a grounded workpiece in most of the cases, and so all the electrons which would come off causing high current between the two surfaces would result in some kind of a local heating, resistive heating across this particular surface, and therefore, in this condition, if I try to disturb this small weldments which have been made by pulling off the electrode back, which normally happens, there is going to be a shrinkage in that particular area of the bridge which has been formulated, and slowly there would be a case where the electrons which are actually flowing now at a higher and higher density, because obviously as the bridge is trying to separate out the area between the two bridges, becomes lesser and lesser. Okay. And so, there is a state where the current density is so high that the electron almost starts boiling off the material, and such boiling would result in something which would ionize a layer of gas which is close by, and this we know as a arc. Okay. So, there is a boiling of the electrons from these small asperities as the area has reduced, and as you are increasingly trying to separate the electrode from the workpiece, and because of the boiling the electrons start coming off the metal into the surrounding gases, start ionizing the gases. And so, there are two different kind of electrons which are there typically in the state which results. One is obviously the primary electron which has been emitted by the electrode in a close vicinity or in a close space, and the other obviously is the gases which are in the medium which get ionized because of these electrons, and some of the collisions may be completely inelastic in nature, and they may result in some kind of additional electrons. So, you have ions and electrons which are formulated, and so it is like a plasma, it is like a hot plasma which has been formulated in some in a zone like this. So, therefore, there are many electrons which are coming out, and there are many ions which are there, and as you increase the distance of the electrode from the metal, this arc kind of increases to an extent when to an extent that the VI relationship between the source which has a finite power and the requirement of this kind of a arc stricken medium would balance out each other. Okay. So, up to that extent the arc would stay, and beyond that, if you again increase the separation between the electrode and the workpiece any further, the arc would kind of cut off or extinguish, because now the power requirements of the arc would not be able to get supplied by the power source that is giving power to this electrode work combination. So, again in summary, what is going on, then the electrodes getting very close, generating small asperities as there is a large current, almost a short circuit level current which is flowing, and then you trying to increase the electrode distance, which is resulting in some kind of again area minimization between these asperities. The plastic welded asperities are going to get now separated back, and because of the area minimization, the current density increases locally and starts giving rise to a situation where there is electron boiling of these asperities, and this boiling basically ionizes the gas medium around, and it starts building up the arc of high fast moving gas atoms and electrons in the space between the electrodes. Okay, so, that you see as the glaring region which comes between the electrode and the work in such welding processes. So, let us just look at some of the physical aspects, or let us say physical values which are formulated. Obviously, the electrons having negative charge coming out of the anode would be pulled back, whereas those coming out of the cathode would also be attracted towards the anode, and the rate at which the electrons are emitted from the hot surface is given by this characteristic equation I equal to c theta square exponential minus beta by theta, where I is in ampere per centimeter square. This is the current density level of a particular portion of the surface. Theta is the absolute temperature to which obviously, because of fast moving electrons, the temperature will rise quite a bit, which will result in some kind of melting of the weldment, in which we want to really either melt the electrode in place, or then even just melt the parent region around the arc. C is a constant, and beta is given by this expression here, phi e by k theta. E is the electronic charge, 1.6 10 to the power minus 19 coulombs, and phi basically is also known as the thermionic work function, and it is measured in electron volts, and I will give you a list of thermionic work functions for different materials, and k is the Boltzmann constant in this particular case. So, in fact, the phi value, the thermionic work function value, represents the kinetic energy that is really necessary to start boiling off an electron from a surface. So, the values of some of the phi's are given here for common metals. You have aluminum, copper, iron, tungsten, sodium, potassium, nickel, and the ionization potentials, and this phi, the work function values in EV are given as 4.1 to 5.0, as you can see for the various materials. It is obvious that, as the equation says, beta equals phi e by k theta, and also the current density I equation says c theta square exponential minus beta by theta, an increase in theta would obviously, and also a reduction in the phi maybe, would obviously result in a case where the current densities become huge, okay, and it makes, you can say, the emission of the electrons much easier. So, with a lower work function value and a higher absolute temperature, the electrons would ooze out more easily, thus contributing to a higher level of the current density. So, the current per unit area becomes more and more because of the simultaneous reduction of the thermionic work function and the increase in the absolute temperature. Once started, the arc itself becomes a source of ions through the process of ionization. So, obviously, there are going to be gas metals which gas ions which are or gas atoms which are going to be there in the space, heated up, and they are fast moving because of the turbulence created by some of the electron ions which are generated close to the cathode and anode, and it results in again few more secondary electrons and secondary ions generating in the process. And so, you have a conducting column of the arc which is created. Okay. So, the ions obviously are attracted in this case by the cathode, and the resulting collisions keep the cathode filament quite a bit hot. In fact, there are many secondary electrons generated because of the collision of such ions into the cathode. Similarly, the anode side is more like an electron sink, so it will observe all the electrons here, but you have to understand that because of its anodic nature, there is already a layer of electrons very close by, and any new electron which is coming to go to the anode should have to pass through this layer of electrons which are again close by. So, therefore, there is a huge drop at the anode and at the cathode surfaces, whereas towards the, if you look at the drop along the arc, then it will not be that sharp, and as a result we can actually characterize the voltage versus length in case of the arcs to be very sharply drooping across the cathode and anode, and less drooping in nature across the bulk of the arc. So, we will actually do a section when we will try to introduce all these things here. The total arc current is carried by two sets of electrons that I had earlier mentioned. First set is emitted by the cathode directly, it is called primary electrons, and the second set is known as the secondary electrons, and is produced as a result of the ionization of the arc gap. And so, based on whatever material combinations you are using, for example, you may use primary electrons, you may use, let us say, tungsten and carbon electrodes, or aluminum electrodes, or copper electrodes. So, with tungsten and carbon electrodes, normally the primary electrons carry the majority of the current, whereas with the aluminum or the copper electrodes, it may be the secondary electrons which carry majority of the current. So, it really depends on what is going to be the work function value and the theta value of the arc, where you are placing the arc, okay, in terms of its creation. So, an electron of charge E moving in an electric field of let us say capital E value would obviously express a force small e into capital E, and if this moves with the distance d, so the total amount of work which is done, which is also equal to the kinetic energy of the electron, can be represented as E by d. It also moves with an acceleration E by m, where m is the mass of the electron, but obviously this kinetic energy is the reason why the temperature would rise up and cause many such secondary ions and electrons to formulate in an arc column. So, let us talk about now the arc structure and characteristics. So, as I already told you that on the cathode there is a spot from which this electron emanation process happens, and this is relatively a very small area on the cathode surface, and we also know it as a cathode spot, and this is the really the causative area or region for emitting all the electrons. Okay. So, that is what we know as the cathode spot. Similarly, we have cathode space which is a gaseous region adjacent to the cathode, has a thickness of the order of about 10 to the power of minus 3 centimeters, about close to 10 to the power of minus 5 meters, about 10 microns. So, this region has a positive charge space, obviously, because you have cathode which is highly negatively charged. So, it will attract all the positive ions near to it. Okay. So, there is a region which would be filled with positive ions, this being the cathode side, and a voltage drop obviously in this region is necessary for the electrons to be pulled across this region, because you have positive ions, and if once the electron goes into this particular space, it is very hard for the electron to get back into the negative cathode. Okay. So, there is a drop suddenly in the energy of the electron the moment it goes into the positive space around the cathode. So, similarly, there is following this is an arc column, which is again the visible portion of the arc consisting of the hot ionized gases or plasmas, where the voltage drop is not very sharp, and I will actually comment upon this how with length the voltage would drop in just about the next section of this particular module. And then obviously, you have the anode space, where a similar problem, but again the anode being positively charged would attract negatively charged electrons, okay, around it. So, there is a space which would contain negatively charged electrons, and it is very difficult for the electrons otherwise in the medium to penetrate through this negatively charged region in order to go to the anode side. One of the reasons why there is again a very sharp drop across this anode region, and then obviously in the anode whatever around whatever region this spot gets formulated, we know as anode spot. So, this is really the section across which there is an electron flow or a current flow on the anode. So, if you look at the voltage characteristics and how in the arc space the potential can vary, we have a huge drop at the cathode because of obvious reasons as told earlier, huge drop again of potential across the anode, and then relatively smaller drop across the main column of the arc, and that is how you would actually characterize the arc space. So, now let us look at how the voltage would vary as a function of the current across the arc, and if you look at the way that the arc builds up, there are many interesting things associated with the build up process. So, at the beginning up to like let us say about 50 amperes of current, the arc is more or less cylindrical in nature. Okay. So, if I really looked at the surface area to volume ratio of a cylinder, let us say we have a cylinder here, okay, and your length of the cylinder is L and the diameter of the cylinder is D. Okay. So, the surface area is pi d L and the volume is pi d square by 4 L. So, obviously, the surface to volume ratio in such a cylinder happens to be about close to 4 by d. Okay. So, as the d increases, obviously, the surface to volume ratio would decrease. So, supposing now if I had a case where the d is increasing of an arc, but the cylindrical constitution of the arc is carried forward, and this happens only up to about 50 amperes of arc currents, where the arc formulated still is about close to cylindrical in shape. So, the surface to volume ratio reduces with an increase in diameter. So, if there is a thicker arc, for example, it will have a lesser surface area in comparison to a thinner arc, okay, and a thinner and longer arc. So, because of all these reasons, what typically would happen is that because surface area also is a function or is like directly proportional to the rate of the heat transfer. If the surface to volume reduces, then the volume or the bulk of the arc which is containing all these gases and electrons and is also a cause of the temperature rise, would be able to rise the temperature to quite a reasonable value, but the surface area being smaller in comparison to the volume may not be able to dissipate that heat much. So, it is a hotter arc. Okay. So, a thick arc is always a hotter arc because the dissipation available because of the decrease in the surface to volume ratio decrease. So, the heat transfer across the arc may not, or from the arc into the environment may not be so huge in comparison to the heat addition to the arc because of these ionization effects which come in the space for the same. So, therefore, below 50 amperes you can consider that as the diameter of the arc increases, and that would happen as a function of the voltage, the conductivity of the arc, which is also a function of the temperature of the arc, would actually increase, and because of this the resistance will decrease, and because of this the current value may decrease at a certain voltage. So, if the voltage reduction delta V by delta I, if we consider if the resistance is decreasing as a function of the thickness of the arc, so obviously the delta V by delta I will also be sort of decreasing, meaning thereby that this part of the characteristic is showing that particular change. So, the as you see, this portion up to 50 amperes is basically a drop in the resistance, because of which even if the current increasing, the voltage is not seeming to increase. Beyond 50 amperes, the curve, the cylindrical characteristic of the curve is not maintained anymore, and there is a gradual bulging of the arc length. And so, the total length that the electron has to travel would increase because of such bulges. So, for a very significantly long time, both the effects of the resistance going down because of the hot arc and the fact that the arc is bulging and there is additional path length that the electrons have to cover continues. So, that you can see that up to quite a bit of current value anymore, you are not having any significant change in the voltage. So, they are kind of compensating for each other, but beyond that, then what happens is that the bulge part of the arc, that means the arc getting stricken like this, would increase more path length in comparison to the heat transfer process, the contribution of the heat transfer process, and there is a slow increase of the voltage with respect to the current beyond that. So, that is why this characteristics, that at the first before 50 amperes, the increase of the cylinder size of the arc and the reduction in the surface area would result in a hotter arc, and beyond that there is some kind of a balance between this heat retained vis-a-vis the path length increase because of bulging of the arc, and then there is a predominance of the path length increase of the bulging part. So, that the again the V versus I becomes a linearly rising trend. So, with this I would like to end this particular module, but in the next module we will try to look at that how you can have these arc characteristics of voltage versus current as a function of length to be interspersed with the voltage current characteristics of the power source, so that we can talk about operating points of the welding system. So, with that I would like to close this particular module. Thank you so much.